Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to give an introduction to the labs for NE 216, Advanced Calculus 1 for Nanotechnology Engineering, and we're going to look at some of the techniques used in numerical analysis and floating point numbers. So in this topic we're going to look at 5 tools that are used quite commonly in numerical analysis, specifically iteration, linear algebra, interpolation, Taylor series, and bracketing. We'll then review Landau symbols and then focus on the floating point number representation of real values. Finally, we'll review the topics that will be covered in the NE 216 and 217 labs. Specifically, we'll be looking at initial value problems for this course and boundary value problems for partial differential equations in NE 217. So many numerical analysis routines use one or more of the following tools: iteration, linear algebra, interpolation, Taylor series, and bracketing. And in fact, all of the algorithms that you saw in your first year numerical analysis course use some combination of these techniques. Now, iteration is a tool that is used by almost all numerical algorithms. We have a problem. We're trying to find a solution, x star. What we're going to do is we're going to start with an approximation to our solution. We're going to call that's an approximation or a guess. We're going to call that x naught. Then we're going to develop an algorithm. What does this algorithm do? Well, given an approximation to x star, the algorithm is going to give us a new point that's slightly better. So basically, given x sub k, the algorithm will give us a next approximation, x sub k plus 1, which is hopefully a better approximation of x star than the previous value. So if we're going to apply such an algorithm where we start with an initial point and keep on applying an algorithm to get closer and closer to the solution, we have some questions that we have to answer. At what point is our approximation good enough? And also, what happens if the algorithm fails? At what point do we stop if we just realize that there's very little likelihood of the algorithm actually converging? So one of the most obvious and simple applications of iteration is with the fixed point theorem. The fixed point theorem says that if we have an equation of the form x is equal to f of x, then if around a solution to that there's a local contraction mapping, then we may find or approximate that solution by starting with an initial guess, or given an initial guess xk, we can evaluate x sub k or evaluate the function at the point x sub k and assign that to the next value x sub k plus 1. So now we're changing an equation into an iterative technique. Take x sub k, evaluate f at that point, and assign that value to the next point x sub k plus 1. So let's take a look at an example. Here we have the equation x is equal to cos of x. I'd like to find out what value satisfies that. Here's a graph of y is equal to cos of x. Here's a graph of y equals x. They intersect at this point, and that intersection point is a solution to that equation. Using MATLAB, we get an approximate value of that point, and taking the average of those two values, let's start off with an initial guess of x is equal to 0.7388. So the next step that we do is we take the initial guess, let's assign it to a variable x, and now we will iterate 20 times. I will evaluate the current value of the variable x, evaluate cosine at that value, and assign it back to x, and then continue iterating, and hopefully it will converge to the solution x star. Well, you'll see that after 20 iterations, yes, we get slowly appear to be converging. We get more and more digits of precision that are getting closer and closer to the solution x is equal to cos of x. However, there are other numerical algorithms as well. For example, if you reinterpret the problem as if it was a root finding problem, then you can apply Newton's method. This is the application of Newton's method to the same problem, reinterpreted, And now, after only 2 iterations, we get as much accuracy as we have precision with the double precision floating point representation. That's as good as you can get, at least in MATLAB. So there are some algorithms will be better than others. Now note, there's no such thing as a perfect algorithm either. No algorithm can take an arbitrary random point and converge on a solution, except for maybe the most trivial of problems. Consequently, you as an engineer have to have a really good idea as to what your answer should be anyway. If you don't know what the answer should be as an engineer, then perhaps the problem is not with what you're trying to solve, but the problem is with you. You should know approximately what you're trying to find. In this course, for the most part, you're going to be given the initial points or the initial values, unless we're actually posing a question where we're actually explicitly asking you to estimate such a value. Okay, iteration. Next tool is linear algebra. Now, you've seen linear algebra already in your first year, and most interesting systems contain more than one variable. Now, when we're trying to approximate solutions to more complex systems, then this ultimately results in a system of either nonlinear or linear equations. If we have a system of linear equations, no problem. We just apply Gaussian elimination or something like that, and we get a solution. However, in reality, most equations will not be linear. They're going to be nonlinear equations. So the only thing we can solve is a system of linear equations. So what can we do? Well, in most cases, what we do is when we're hit with a nonlinear equation, what we do is we approximate the nonlinear equation by a linear equation. Having done so, then we can solve the linear equation and then iterate. This is exactly what Newton's method does. Newton's method essentially says, I want to find the root of a nonlinear function f. How do I find it? Well, I have an approximation to that root, x sub k. At that point, I'm going to find a tangent, a linear line, or a line that passes through the point that is tangent to the curve. And Newton's method says, if I find a root of this line, the root of that line will be a better approximation of the root of the function than the original approximation x sub k. Well, how does that work? Well, again, if we have a line with slope m passing through those 2 points, this is the equation of that line. If I want to find a root of a linear equation, well, I just set it equal to 0 and solve for x. Solving for x gives us this expression. Well, in terms of Newton's method, y of k is just the function evaluated at x sub k, and the slope is the derivative at that point. So we've converted a nonlinear system into a linear system. We won't be covering in this course, but you can actually do this for systems of nonlinear equations, where you convert a system of nonlinear equations into a system of linear equations and find a simultaneous root of all of the equations. Now, once we start looking at larger systems, you're going to see that Gaussian elimination isn't that efficient. It's actually quite slow once we start dealing with very large systems of linear equations. Say you're trying to simulate a circuit, that might be a 1,000 by 1,000 system of equations. Or if you're trying to simulate a processor, that might be over 1 million equations in 1 million unknowns. Sparse, but still very large. Gaussian elimination is not efficient. Instead, there are iterative approaches for finding solutions to system of linear equations. One of the worst is the Jacobi method. It's not very useful, it's very slow, but it's instructional. I want to solve a system of linear equations. A known matrix M times an unknown vector b, x, equals a known vector b. Let's rewrite M as the product of a diagonal matrix. So let's just take out the diagonal entries of the matrix. And then let's take all of the off-diagonal entries of that matrix and assign that to the matrix M sub off. So the matrix M is the matrix of the diagonal entries plus the off-diagonal entries. Let's just expand that. And now let's take this term onto the other side. Now I have a diagonal matrix times x is equal to an expression. Finding the inverse of a matrix is a very expensive, computationally expensive problem. It's also numerically unstable. However, if we have a diagonal matrix, it's a lot easier. The inverse is just the matrix containing the reciprocal of the inverses of the entries on the diagonal. What's easier than that? So I can find the inverse of the diagonal matrix D very quickly, assuming all of the entries are non-zero. Let's multiply both sides by the inverse of that matrix. So now we have x is equal to an expression. Now, all I did was apply algebra in all of these cases. So a solution to this equation is equal to a solution to that equation. However, what does this now look like? It looks like the fixed point theorem. X is equal to f at x. What did we do there? Well, we just started off with a random, or started off with an initial vector x, applied this expression to x, and that was our next approximation. And we kept on doing that. We're going to do that right now. It's reasonably straightforward. This defines, here's our matrix, here's our known vector of knowns. We can enter them into MATLAB. I can extract the diagonal matrix quite quickly, just called diag twice. The first time I get back a vector of diagonal entries. If I pass diag a vector of entries, it creates a diagonal matrix with those entries on the diagonal. I can subtract the diagonal entries off of the matrix M to get the matrix of off-diagonal entries. So I want to find this solution to this problem. How am I going to start out? What do I use as an initial value? A vector of zeros? Possibly. However, let's be a little bit smarter about this. Assume that all of the off-diagonal entries are 0. So let's just take the diagonal entries, and essentially let's take the matrix D times x is equal to B, and let's solve the system D times x is equal to B. Well, because D is a diagonal matrix, this is quite easy. The solution is just the inverse times B, and finding the inverse is quite trivial. So now we have our initial approximation, and we can see it's not very good. The first entry itself has a relative error of over 100%, but it's at least within the same ballpark. All the values are at least within an order of magnitude. So let's iterate. Let's start with this x value, and let's apply the right-hand side. Multiply x by the matrix of off-diagonal entries, subtract that result from the vector b, and then multiply all of that by the inverse of the diagonal matrix. Initially, it's not all that great, but at least the first entry is no longer off by more than 100% relative error. The other values, again, are also slowly appearing to converge. If you iterate a few more times, you will see that more and more of the values, or we get more and more accuracy in each of the entries of the vector. So in theory, we could continue iterating. However, the Jacobi method is a very slowly converging algorithm. Gauss-Seidel is slightly faster, but there are even faster techniques such as gradient descent, and there are residual methods. There's an excellent book by Yosef Saad which covers all of these very fast, iterative approaches to solving systems of linear equations. Next, let's look at interpolation. Given a set of points, one question that we're always trying to find is, can we find a best fitting polynomial that passes through those points? Now, if we have 2 points and we want to find a straight line of the form y is equal to ax plus b that passes through those points, well, that's quite straightforward. I have 2 points, and I can trivially find a line that passes through them. Not a problem. How do we find the values of a and b? Well, let's just substitute x is equal to 2 and y is equal to 5 into that expression, or that equation. That gives us one equation. 2a plus b is equal to 5. If we substitute x is equal to 7 and y is equal to 8, we get a second equation. It's a system of 2 equations and 2 unknowns, linear algebra. So we can solve this system, and because of the location, the first entry is the value of a, the second solution is the value of b, and therefore the best fitting line that passes through these 2 points is 0.6x plus 3.8. Now, there's also a theorem that says if I have n points where each of those n points has a unique x value, then it's guaranteed that we can find a unique interpolating polynomial of degree n minus 1 or less that passes through all of those n points. Like, for example, if I have 4 points, this theorem says that I must be able to find a cubic polynomial that passes through them. A cubic polynomial is the form y is equal to ax cubed plus bx squared plus cx plus d. Well, once again, substitute x is equal to 2 and y is equal to 6 into this equation. That gives us one equation. Do the same for the second, third, and fourth point. That gives us 4 equations and 4 unknowns. This is a system of linear equations. Essentially, it's this system here once we evaluate everything out, and we have a vector of unknown coefficients. That's what we're trying to solve for, a vector of unknown coefficients. The first entry will be the coefficient of the highest polynomial term, x cubed. The next coefficient, or the next entry of the vector, is the coefficient of x squared. The third is the coefficient of x, and the fourth is the constant coefficient. So we can plug this into MATLAB, we can solve, and so therefore we have this term times x cubed plus 1.4 times x squared minus this term times x minus the constant coefficient. But don't trust me, you can actually check your answer in MATLAB. Here we're plotting the 4 points, the x values, the y values, as red circles. Then I'm going to create a vector of values going from negative 2.5 to 5.5. Now in MATLAB, if a vector contains the coefficient, well, MATLAB will always interpret a vector as a polynomial, if necessary, where the first term is the highest coefficient and the last term in the vector is the constant coefficient. So a vector of length 5 represents a quartic polynomial. The first entry is the coefficient of x squared. The last coefficient is the constant coefficient in that vector. And polyval makes that assumption, so I can now evaluate each of the values in my vector of x values at this polynomial. That gives me my y values. I can plot the x and y values, and we see that this cubic polynomial does in fact pass through all 4 of the points precisely. Now, the fourth tool in numerical analysis is Taylor series. How did you find Taylor series? Well, again, you recall that in your calculus course you may have found an interpolating polynomial and then let the distance between the adjacent points go to 0. So the distinct points in the limit became a single point, and that gave you a Taylor series approximation of the function around the point x naught. Now, we can truncate the Taylor series. In this case, we have a third order truncation. So f at x is equal to this approximation plus an error term. And the error term is determined by evaluating the third derivative at some unknown point xi between x naught and x. So some point on that interval, for some point on that interval, evaluated at the third derivative gives you an exact solution. Again, assuming that the function is infinitely differentiable. In numerical methods, however, we don't have 2 points x naught and x. Usually we are focused on a single approximate value, and we'd like to know how the function behaves in a small neighborhood around that point. So we might be interested in x minus h or x plus h for very small values of h around that point. In this case, we can rewrite the Taylor series. Now the Taylor series looks a little bit simpler. So in this case, we have f at x plus h is equal to f at x plus the derivative times h plus a half times the second derivative times h squared plus a sixth times the third derivative at that point times h cubed, and so on and so forth. In this case, we can also truncate. In this case, let's truncate to a second order approximation. And so now f at x plus h is equal to f at x plus the derivative times h plus an error term. The error term is the second derivative evaluated at xi, where xi lies somewhere in the interval from x to x plus h. So this will be a very good approximation if both the second derivative is reasonable in size and h is small. If h is small, h squared is even smaller. And so this is actually a good approximation for f at x plus h. We're going to be using this in a number of cases. The fifth tool, which we won't use in this course but is useful to describe, is bracketing. Under certain circumstances, you can determine that there's a solution to a problem on an interval. The bisection method, for example. I know there's a solution on the interval a to b. What the bracketing does is choosing a point between a and b, some point c, and this gives us a choice of either choosing the interval ac or the interval cb. Our algorithm chooses which of those two intervals we continue iterating on. We continue iterating until the width of the interval is sufficiently small, and then we choose the endpoint which best satisfies the condition of our problem. This is the most inefficient of the methods and can be actually quite expensive in higher dimensions, but in some cases it's the only one that's actually guaranteed to converge. So we've summarized 5 tools used in numerical algorithms: iteration, linear algebra, and we used iteration to solve systems of linear equations. Interpolation, we found interpolating polynomials using linear algebra. Bracketing, or Taylor series, is just the limit as the distance between the points goes to 0 of interpolating polynomials. And finally, bracketing. Next, we're going to look at Landau symbols, floating point numbers, and then look at future topics. So we're going to be using Landau symbols. Now, when iterating or finding an approximation, we're often going to end up with a situation where some value h, describing some quantitative measurable variable in our problem, gives us some information about the error. For example, in some algorithms, if we make h smaller by a factor of 2, the error itself drops by a factor of 2. In other cases, h may actually represent the error, and the error on the next iteration is h squared. That's Newton's method. If the error is initially 0.001, after the next iteration the error will be some scalar multiple of 0.001. 0.0000001. You can see why it converges so quickly. How do we represent this? We're going to use the big O notation, or the big O Landau symbol. So an algorithm is going to be said to be order h with respect to this value h if the error is proportional to h, and so therefore reducing h by half reduces the error by half. If, however, the error is proportional to h squared, then we will say that the algorithm is order h squared, and now reducing h by half reduces the error by a factor of 4. Reducing h by a tenth, or by a factor of 10, reduces the error by a factor of 100. In one case, we're going to see that the error depends on h to the fourth. Having h actually reduces the error by a factor of 16. Reducing h by a factor of 10 reduces the error by a factor of 10,000. So again, it's a useful mechanism for describing how quickly various algorithms converge. So the next topic we're going to look at is floating point numbers. And the majority of Lab 1 will deal with the floating point representation. Why do we have this floating point representation? Well, we're dealing with real values. Every single differential equation assumes continuity. It assumes we have real numbers, not even rationals, but real numbers. Differentiation is a limit with respect to real numbers. But every time we represent real numbers on a computer, we can't. We can only store a finite number of digits, and consequently we are going to run into problems. If we only store a finite amount of precision on the computer, we have issues. We're no longer using exact values, we're using approximations. And we're iterating on approximations. And we very quickly lose certain characteristics. We even lose associativity. Normally you think, oh, x plus y plus z. It doesn't really matter if you add x and y first and then add z, or add y and z first and then add x. But with floating point numbers, it actually can affect the result. So basically what this says is that we also have to make sure that we carefully design our algorithms not only to deal with numerical approximations, but also to deal with the fact that we're using a finite precision floating point representation of real numbers. Now, the double precision floating point format that you use in MATLAB, whether you know it or not, or in C, if you declare a variable as double, all of those variables behave as if or are defined by the IEEE 754 standard. The creation of this standard decades ago was led by Dr. William Kahan, and this was one of the most successful examples of collaboration. Basically, this committee got together. Each of them came from various companies, each using their own floating point format within their computers, each of them having good reasons to justify having their standard put into the IEEE standard. However, instead, they managed to create a standard that took the best characteristics of all of the various floating point systems, and it was superior to all of them. What this means is that we can actually trust doubles up to a well-defined point as defined in that standard. However, some people will try this. In MATLAB, or even in C++ or C, try 1 minus a half, or 1 minus 2/3 minus 1/3. That should be 0, but it's not 0. And then they claim, oh, floating point numbers don't work. Floating point numbers are not exact representations. I cannot represent 2/3 and 1/3 precisely using floating point numbers. Instead, I must truncate at some point. With double precision floating point numbers, I store 53 bits of precision. After that, I have to round any other values. So let's see what happens. If I subtract 2/3 off of 1, well, there's a 0 here. I'd have to do a number of carries. 10 minus 1 is 1. 1 minus 0 is 1. 1 minus 1 is 0. So you get that errant 1 here that doesn't match the pattern. It's not the best approximation of 1/3. It's slightly off. Why is that? Because we had an error introduced when we represented 2/3 by a finite binary representation, and we also had an error in our subtraction. Next, or that introduced an error into our subtraction. Next, if we take this result and subtract off of that 1/3, notice the last two digits don't line up, and therefore there's that errant 1 there. It's in the 54th position after the radix point. So essentially what's going to happen is that 1/3 minus 2/3 minus, or 1 minus 2/3 minus 1/3 is going to give you 2 to the negative 54. And if you calculate it, that's exactly what you get. So floating point arithmetic is not exact. Every operation, including when you're approximating a real number by a floating point approximation, is going to have some sort of error. Under some conditions, the error must be guaranteed to be less than 0.5 in the last digit. For function evaluations, such as trigonometric functions, there's a slightly larger, but still reasonable interval on which that value has to be. So before we can define, or at least look at the IEEE representation, we're going to try to build up something that's similar to the IEEE representation by coming up with reasonable requirements and criteria for such a representation. To do this, we're going to have to define absolute and relative error. So if A approximates some value x, we will say that the absolute value of the difference of the two is the absolute error of our approximation A. If we divide that by x, that is the relative error of A, and if we multiply that by 100%, that is the percent relative error of A. Usually we use percent more colloquially. Now, absolute error is usually not very useful. If I told you that a solution had an absolute error of 1 millimeter, how useful is that? Well, on a trip to Mars, it's probably insignificant. If you're actually using that 1 millimeter to define some specification on the Mars rover, that probably is significant, most likely, but maybe not. However, if you're dealing with a nano system, if you're dealing on nanometers, an error of 1 millimeter is going to be catastrophic. On the other hand, relative error is unitless. So it doesn't care about the units. It's a relative measure. And for most cases, 0.001% relative error is often more than good enough in many engineering situations. Indeed, in some cases, it might not be even possible to achieve that level of accuracy. In other cases, it may actually be necessary to have more precision. But in that ballpark is approximately where acceptable relative error for engineering applications is, at least for the final solution. So how are we going to store real numbers? We're going to store them with a finite number of digits. For example, we could approximate pi by 3.14. Not a very good approximation, but it's the approximation every child uses in elementary school. So this gives us an idea as to the first constraint. Any representation of real numbers in the computer must use a fixed amount of memory. So all numbers will be represented by the same number of digits or same amount of memory in the computer. We also want to be able to represent large numbers and small numbers. So 0.0001 we should be able to represent, but we should also be able to represent a million. We also want to represent all the numbers on our range with a very small relative error. We should not be representing numbers with significant relative error anywhere on our range. We should also be able to quite quickly test whether or not two representations represent the same number or represent different numbers. And we should also be able to compare relative differences quite easily. Is looking at two representations, is this the larger one or is that the larger one? And we should be able to do that quite quickly. So here's my space requirement. I'm going to constrain us to 6 decimal digits of accuracy. Or sorry, 6 decimal integers. Every number that we represent has to be represented with 6 decimal numbers, and we allow a sign bit. How could we do this? Well, a fixed point representation would simply say, well, the decimal is here in the third location. So these 6 decimal numbers represent that value. So for example, 0.39432 represents 39.432. On the other hand, if I want to store negative 3.14152, well, here's the decimal point. There's only one digit to the left of the decimal point. I take the next 3 digits after the decimal point. I can round up because this is 52. So I would store this as 003142. Now, how good is this representation? Well, the range is not very good. I can only store numbers from 0.001 to about 1,000. I can't even store 10,000 or 2,000. Also, the relative error can be far too unacceptably large. If I try to store 0.0015 in this representation, I can't do it precisely. I have to round up to 0.002. Now this point is on this interval, but our representation has a relative error of 33%. On the other hand, 999.9985 can be represented by 999,998, and that has a relative error that's very small. The percent relative error is 0.00005. That's really good. Unfortunately, that error is probably unacceptable. So we have limited range and other issues. Now, one nice thing is, on the other hand, relative magnitudes can be computed quite quickly. This as an integer is smaller than this as an integer. Therefore, the number it represents is smaller than the number that this represents. What's easier to do than compare digits to see which is larger? However, the first two issues are too catastrophic. Let's have a different floating point representation. The 6 digits are going to be interpreted as follows. The first 2 digits will represent an exponent, but the actual exponent is the first 2 digits minus 49, and we'll see why that's necessary. The next 4 digits represent a mantissa, where the first digit, m, must be non-zero. And so therefore, this represents plus or minus m.nnn times 10 times 10 to the e to the 5th EE minus 49. Let's see how good this is as a representation. So, as an example, 54,9238 represents 9.238 times 10 to the 5, or 54 minus 49. So already we're representing a number that's almost as large as 100,000, and doing so quite easily. On the other hand, if I want to represent 372.863, well, I would have to round to 4 decimal numbers. That would be my mantissa, and this would be 3.3 729 times 10 to the 2. What do I need to get? What subtracted off? What, when 49 is subtracted off of these, gives you 42, or gives you 2? 51. So 513729. How does this fare? Well, first of all, we can represent very, very large numbers, or very small numbers. If the first two digits are 0, then our exponent is 10 to the negative 49. That's incredibly small. So for example, here, this number represents 5.723 times 10 to the negative 49. On the other end, if the first two digits are 99, those are very large numbers. Those are numbers as large as 10 to the 50 and larger. So for example, 995723 represents a number represents 5.723 times 10 to the 50. That is a very large range. Not only that, every single number on the range from 10 to the negative 49 all the way up to 9.999 times 10 to the 50 can be represented by one of these values with a relative error no larger than 0.05%. Any number. For example, the population of Canada a few years ago on the census can be represented by 56, because it's times 10 to the 7. 3348. 33476, we round up to 3.348. The relative error of that representation of this number is less than 0.01%. Let's take Planck's constant on the other hand. 6.626 times 10 to the negative 34, well, 15 minus 49 is negative 34, so this is represented by 156626, and that has a relative error that's even smaller. The relative error is on the order of 0.001% relative error. Now, there are two things that we required. We required that the first two digits represent the exponent, and then we subtracted off that 49. That 49 is actually called a bias. But also we required that m was non-zero. Now, why would we require that m is non-zero? Well, the issue is if m is allowed to be 0, notice that all four of these representations represent 1. Why is that? Well, this is 1.000 times 10 to the 0. This is 0.1 times 10 to the 1. This is 0.01 times 10 to the 2, and 0.001 times 10 to the 3. All of those represent the same value 1. It would be catastrophic if, just to compare two floating point numbers to see if they're equal, we would have to do some sort of mechanical operation to do that. So by requiring m to be non-zero, it guarantees that we can very quickly compare two numbers just by looking at their representation. Not only that, by choosing the exponent first and using a bias, as opposed to say 2's complement, or 10's complement in this case, relative comparisons are also very fast. Now here are four representations of numbers. Which of these represents the largest actual real number, and which represents the smallest? Well, fortunately, just like before, all we do is look at the relative magnitude as integers. This is the largest, this is the next largest, that's the next largest, and that's the smallest. Well, the actual numbers they represent also follow that order. Why? Because this number here is 6.729 times 10 to the 36. This number is 3.823 times 10 to the 57 minus 49, or 10 to the 8. So that, of course, is smaller than the first one. What's next? This one here, 9.657 times 10 to the negative 11. And finally, we have 5.537 times 10 to the negative 30. So we can even compare relative magnitude without caring what the actual value it represents. We just compare the digits in order, and whichever is larger as an integer, that is also represents the largest value. Now we have a few more issues. Notice that we could potentially have two zeros, a positive 0 and a negative 0. Do we want them to be equal, or do we want them to be different? Well, actually, we do want two different values of 0. We want positive 0 and negative 0, because remember, these don't represent 0. 0 represents every number on the range from negative s to s, where s is the smallest number that can be represented by a non-zero floating point representation. So 0 does not represent just a single value. It represents everything that's too small that can be represented by any other object in our representation. And this actually has serious consequences. In example, branch cuts. Now you know that ln of negative 1 is j times pi. However, ln has a branch cut along the negative real axis. And so if you go just a little bit above the axis, ln of this value is pi j. But on the other hand, if you go just a little bit below the real line and evaluate the natural logarithm at that point, the actual value is not pi j, but negative pi j. So we actually have a discontinuity. There are certain circumstances, heavy functions as well, where this can lead to serious problems. So the floating point IEEE 754 specifies a signed 0. Also, if you take 1 over 0, is that infinity or negative infinity? Well, if you have positive 0, you can let it be positive infinity. If you have negative 0, you can let 1 over that be negative infinity. There are other issues. Notice that if I take this value here, that value can be represented with absolute full precision using our representation. But here's a number that's only half of the previous number, approximately, and yet that must be represented by 0. So we go from full precision, and then going down by less than a factor of 10, anything smaller than that has no precision. Solution. This is somewhat awkward. We don't want to be able to just divide a number by 2 and go from full precision, 4 digits. Oh, well, we divide by 2, we get 0 now. To 0, that's 100% relative error. So what we can do to fix this problem is introduce something called denormalized numbers. In the special case where 0, 0 is the exponent, then we can actually allow the next digit to be also 0. So what this means is we can represent numbers even smaller than 1.00 times 10 to the negative 49. So for example, this number can now be represented by 10 to the negative 50. Well, that's 0.4853 times 10 to the negative 49. That's 0.485. Our relative error is larger, potentially, but at least we can store with something other than 0. So denormalized numbers are the special case where the exponent digits are all 0, in which case we actually allow the next digit to also be 0. This means we can just slightly, we can approximate numbers slightly smaller than the smallest number that we can represent with the standard representation. The problem is we get larger and larger relative errors as this coefficient gets smaller. So that's denormalized numbers. Also, There's another case. What do we do about infinity? We don't want infinity to generate errors, because in some cases you can actually work with infinity. So we want a floating point representation of infinity. Because it's not infinity, we're just going to call any number that is larger than the largest number that we can represent by our representation as being infinity. So infinity is going to be represented by 99000. Why? Why does this work? Because if it represented anything else, that first value there must be 0. So now we can represent all numbers that are larger than the largest number that we can represent using 99000, and all numbers that are smaller than the most negative number we can represent with negative 9900. So now if we take the reciprocal of 1 over positive 0, we return this value. If we take the reciprocal of 1 over this value, we return positive 0. There's something else interesting, which is there's going to be a few questions on the lab, but what happens if you do a floating point operation such as 0 divided by 0? Well, this isn't infinity, it could be anything. It's an undefined operation. And in calculus, you saw that anything that has a limiting case is a limiting case in 0 over 0. It could be any real value, or it could be infinity, or it could be 0. Consequently, any operation that is ill-defined or indeterminate is going to be represented by something else that's special, not a number. And we're going to represent not a number by 0100. Again, something that's not normally in our representation. Sorry, there's an error there. That should be 0100. Now, all of these considerations and others were taken into consideration when Dr. Kahan and his committee created the IEEE 754 standard. There were conflicts, but they worked together and they produced the most reasonable representation of floating point numbers. IEEE 754 was the first one. IEEE 754 2008 is currently is the current standard used today. Now, what we looked at was floating point representations for 6 decimal numbers. On a computer, we don't have decimal numbers, we have binary numbers, 0 or 1. So the standard actually defines 2 different representations. Float, a single floating point number, and double, a double precision floating point representation. Other than graphics, float is usually unacceptable. As an engineer, you should always use double. So a double precision floating point representation uses 64 bits. A simple single precision float uses 32. With 64 bits, the first value is the sign bit. If s is equal to 0, it's positive. If s is equal to 1, it's negative. The exponent is the next 11 bits. And so essentially, the sign and the exponent are the first 3 hexadecimal digits. So the next 11 bits are the exponent, and the bias in this case is 1023 in binary. This represents the power of 2. Everything else is the mantissa. And remember that in our representation we require that m is non-zero? Well, the only non-zero binary number is 1. So if we're guaranteed that the binary, if the first digit is 1, let's just not store it at all. So in the double precision floating point format, the mantissa represents all numbers after the decimal, and we assume that there is a leading 1 point. So the smallest positive normalized number has this exponent and zeros after the 1. This is a number equal to 2 to the negative 1022, or approximately 10 to the negative 308. That's a reasonably small number. We can even choose denormalized numbers. In the case of denormalized numbers, if all the digits of the exponent are 0, we assume that this now represents a denormalized number, and that can get as small as 2 to the negative 1074, or as small as on the order of 5 times 10 to the negative 324. So again, these are in the floating point specification, and every single system that implements doubles must implement them in this format. The largest positive number is all ones except in the last location, followed by all ones. This is essentially 2 to the 1024, which is approximately 2 times 10 to the 308. So we have a very, very large range on which we can represent numbers. So again, if I type the corresponding mantissa in times 2 to the 1023, I get a value that is stored that's approximately equal to that. If I calculate 2 to the 1024, I get infinity. So it's slightly less than 2 to the 1024. And again, remember in decimal, 1.9999 repeating, base 10 is equal to 2. In binary, 1.1111 repeating infinitely often is also equal to 2. Infinity is represented by the sign bit with all ones, and if the mantissa is not all 0, then that represents some not a number. Normally the first bit there is set to 1. Not a number has some really weird characteristics, and the characteristics exist for good reasons. For example, if you compare two not a numbers, you get back false. So not a number equals not a number returns false. So you actually have to use a special function, is not a number. You can also check if x is not equal to x, and if that returns true, you know that x is equal to not a number. But that's not a nice way of doing it. That's really nasty to the programmer who's trying to read your code, so it makes much more sense to use is not a number. You can even view the underlying representation in MATLAB by saying format hex. So here, pi is 400. Again, that represents the exponent. And here's the mantissa, all digits after that. E to the 1, again, same exponent because pi is 3.14, e is 2.7, so they are both between 2 and 4. They're both going to have the same exponent. 1 over 0 gives you infinity, 7ff. 0 is just all zeros, and 1 times 10 to the negative 300 gives you this value, which has a reasonably small exponent. And if you want to go to the binary representation, all you have to do is replace every single hexadecimal digit here with a corresponding quartet of binary numbers. Now, there are still issues. Underflow and overflow, subtractive cancellation, adding large numbers and small numbers, the order of how you perform operations because it's no longer associative. All of these have to be taken into account when we're creating algorithms for numerical methods. We're going to look at only one here, and that is the Kahan algorithm for adding a sequence of numbers. Now, if I just randomly add a whole bunch of numbers, well, sometimes I may add a small number to a large number, and I might lose some of the precision of the small number, etc., etc. So the Kahan method of calculating a sum actually tabulates the additional error, keeps track of the additional error in terms of a carrying value C, and then it allows it to work with that. And you can actually you can look at this algorithm yourself if you want on your own time. But what's really nice is if I compute 10 million random numbers between 0 and 1, and now I calculate what's the sum of these. Well, I get some value. If I ask Kahan, how would you sum these values? Well, I get a different value. Only the last few digits does it differ, but I get a different value. Well, what happens if I sort them first and then add them? Well, if I sort them first in ascending from smallest to largest, I get yet a different number, slightly closer to the actual value. And if I sort them descending, I get again a reasonably bad approximation. So I'm claiming that this is the best approximation of this sum of 10 million random numbers. Do you believe me? Why is this one any more correct than any other value that I've shown there? So basically, am I serious? Do I expect you to believe this? Well, fortunately, I don't. So let's go to Maple. Maple is an interesting system that differs from double precision floating point representations. In Maple, it uses decimal numbers, first of all. So you can say, I want every floating point operation to use 10 digits of accuracy. That's the default, 10 digits. So what I can do is I can implement the Kahan method in Maple, and now I can create, in this case, 1 million random numbers between 0 and 1. I can call the add function. So for everything in this list, add it up. I get this value here. If I sort them first, I get a slightly different value. If I sort them in descending order, I get a significantly different value. And if I call Kahan, I get a fourth different number. So notice that the last 3 digits are different in each of these cases. So which of those is actually most closely, well, which is closest to the actual sum of those 1 million random numbers? Well, fortunately, what Maple allows you to do is change the number of digits of precision. So if I now tell Maple, I don't want you using 10 digits of precision, I want you to use 30 digits of precision, now I can add all of those numbers, but now every single operation does not truncate back to 10 digits, but allows it to grow as large as 30 digits. And the correct answer to full precision is this number here. And what is this closest to? Well, 6356, when rounded to 10 digits, gives you the sum that the Kahan algorithm finds. So the Kahan algorithm does actually give you a significantly better approximation. All right, that's floating point numbers. In the labs, you're going to explore a little bit more about floating point numbers, at least for the first one. We're going to look at 6 problems in the 6 labs in this course. And each lab is going to be divided into 2 parts. In the first week, you're going to get a 1-hour presentation, this one here, which will be also presented in class. The next week is a 1-hour help session where you can ask for assistance in that lab that you've been working on for the last week. The lab will be due the day after. So this is actually an integrated part or approach to your nanotechnology courses in numerical approximation. First year you had your engineering computation. That was your introduction to numerical methods. NE260 in this course is going to focus on numerical solutions to initial value problems, solutions to differential equations with initial values. In the next course, NE217, you will be focusing on partial differential equations and boundary value problems. All of this leads to your course in third year, NE 336, Micro and Nanosystem Computer-Aided Design. So in this the labs in this course will be just numerical algorithms in the double precision floating point format. Next week, or 2 weeks from now, you will see differentiation. Then we will approximate first order initial value problems using Euler's methods and Hoynes' method. Then we'll use first order IVPs with fourth order Runcutta and the Dorman prints. Then we will see a system of initial value problems and higher order initial value problems. So let's say our differential equation is not just the first derivative is equal to this, but say the nth derivative is described in terms of lower order derivatives. Finally, we're going to take the algorithm you wrote here and we're going to use it to approximate a boundary value problem using something called the shooting method. So we're going to convert a boundary value problem into an initial value problem. In NE 217, we're going to see how we can solve a boundary value problem using finite differences. We'll then look at the heat conduction diffusion equation, the heat conduction diffusion equation using the Crank-Nicolson method, the wave equation, Laplace's equation in 2 and 3 dimensions. These were all done in 1 dimension, at least 1 spatial dimension. Here we're now going to look at Laplace's equation in 2 and 3 spatial dimensions. And then we will look at the heat conduction diffusion and the wave equation, both in 2 and 3 spatial dimensions. So at the end of this course, you will be able to quite trivially create these graphics which show a drop falling into a square cup, a drop falling into a round cup, a drop of water. Here we have a single point of heat, a single point heat source that is propagating through an insulated room. And here we have a sequence of heat sources in a line propagating heat through an insulated room. All of these you will be able to generate in your NE 217 class at the end of this sequence. In your third year course, you will then be going into finite element methods, which are even cooler. So in this topic, we've reviewed 5 tools used in numerical algorithms: iteration, linear algebra, interpolation, Taylor series, and bracketing. We quickly described how we will use Landau symbols. We looked at floating point numbers and the IEEE 754 standard, and we had a summary of what you will be doing in these labs and future labs in this course, the next course, and in third year. So thank you very much. Have a good day and good luck with your labs.